Yes, sure.
All right, so I suggest we go with your talk now, and it's on studies performed for the EHN2 Beamline at CERN for the next generation muon beam experiments. So whenever you're ready, you can share your slides.
Okay, I'll just do that. Can you see?
Perfect. You can make like full screen if you can.
Yes. Hopefully this works. Can you see full screen now?
Not completely.
You are in the presenter mode. You have to.
Yeah, there is a presenter view.
Yes.
You have to maybe share the desktop or the window.
Yeah, now my laptop just went blank. Sorry. Okay, it's coming back. So what do you see now?
Black screen.
Ah.
Okay, if this is difficult, I suggest that you can actually go without full screen, because that was okay. Like we could see the slide. Oh yeah, perfect. No, for a second it was okay. Okay.
Yeah, I think it has a little bit of lag, so it's changing.
All right, let's go this way. I think it's the best.
Okay. Sorry about that.
No problem.
Okay. Hello, and I first want to thank you for giving me the opportunity to present here. So I will present the studies performed for the EHN2 Beamline at CERN for next generation muon beam experiments. In 2016, we had the Physics-Beyond Collider study, which had its kickoff workshop. And this was launched to launch an exploratory study aimed at exploiting the full scientific potential of the accelerator complex of CERN. So in this context, the Conventional Beams Working Group was formed as part of the Accelerators and Facilities group. And this was done to perform a number of studies for the proposals that were presented for the CERN North area. Recently, a follow-up program was also approved at CERN, and the updated PBC mandate was presented in the 2021 workshop. So here I include the link to the workshop in case anyone is interested. So in this talk, I will focus on the proposals that were, sorry, you can't see the picture, it seems, or. Can you see the accelerator complex picture actually?
Only the one on the right. The one on the left, I can see it on the miniature slide.
Yeah, I didn't know why it is. Okay. So I will focus on the proposals for the EHN2 Beamline. So on the left, hopefully you can see the accelerator complex with the north area, which receives the protons from the SPS. And this north area has three main experimental halls, which are the EHN1, ECN3, and EHN2. And I will present the proposals for EHN2, which includes Na64, muon, and the future program for COMPASS, which is called AMBER. So Na64 is an active beam dump dark matter search experiment, and it's looking for sub-GeV dark photons, and it's currently housed at the CERN EHN1 H4 beamline. So the idea of Na64 is to tag an incoming electron beam of 100 GeV, then dump it against an active target, which is the ECAV. And if the dark photon is produced, this will carry almost half of the beam energy and go through the rest of the detector undetected. So the signature will comprise of an ECAL energy of less than 50 GeV with a missing energy of more than 50 GeV. Na64 mu is the muon program for the dark matter search, which is looking for a new massive gauge boson, the Z mu, that couples predominantly to the second and third lepton generations. So for NH64 mu, the idea is that they will tag an incoming 160 GeV muon beam. And in case the Z mu is produced, this will carry majority of the momentum. And the scattered muon momentum will be tagged with another tracker. So the signature will be a missing momentum of more than 80 GeV. Apart from dark matter, the additional motivation for NH64 mu comes from the muon G-2 anomaly. So as we saw quite recently, that Fermilab confirmed the previous BNL result of the G-2 anomaly, which showed a 4.2 sigma deviation for A mu compared to the theoretical value. So currently, the most motivated explanation for this discrepancy comes from the beyond standard model physics, which includes either light or heavy particles compared to the electroweak scale. So NH64 mu is designed to decisively probe the former scenario for the light Z mu. And in case of negative results as well, this will be important for further clarifications of the muon G-2. With the NH64 mu setup, it's possible to cover the G-2 favored parameter space with 10 to the 10 muons on target. And this is possible in the EHN2 Beamline within a month running time. So this is sort of the setup for NH64 mu, which requires a high intensity focus 160 GeV muon beam in EHN2. The setup is about 15 to 25 meters long, and transversely it's 120 by 60 centimeters. For 2021, they aim to do a test run with a minimal setup of 13 meters, which is shown here. Next, we move to Muoni. Muoni aims to investigate the hadronic contribution to the vacuum polarization in context of G-2. So again, following the Fermilab results, their final aim is a 5 sigma deviation for the standard model muon G-2. And the uncertainty on the theoretical prediction of the hadron contribution, mu, will then be the main limitation for when the future experiments reach their precision. So Muoni aims to determine the hadronic contribution of mu from the scattering data. They aim to measure the hadronic contribution of the running alpha T from the shape of the elastic scattering process by using the muon beam on a target. So they plan to use the muons on the atomic electrons in a low Z target. And the final goal is to determine the differential cross-section with a precision of 10 particles per million, which would lead to a 0.3% statistical error on the mu, on the hadronic contribution of mu. They have presented a letter of intent with the estimated performance from the simulations, and you can find the link here as well. So this is the setup for Muoni, which includes the beryllium target of 1.5 centimeter with 3 pairs of silicon trackers. Each station is about 100 centimeters. And they actually plan to use 40 stations for their complete setup, followed by an eCal and muon filter for their particle ID and background suppression. So their full setup is 40 meters long, but in 21, they aim to do a pilot run with up to 3 stations and an eCal, which would then require a space of about 7 meters. Finally, we have the proposal from the successor to the COMPASS experiment, which is a QCD facility and named AMBER. We have heard many talks throughout this conference from COMPASS, and they have a very rich QCD physics program, which is summarized in this table. They aim to address fundamental issues for strong interactions in a medium and long-term future, and the proposed measurements actually cover a wide range of Q square. In the first phase, they mainly concentrate on the measurement of the proton charge radius through the elastic muon proton scattering to address the proton radius puzzle. Then studying the pion structure via the Drelian process to address the emergence of proton mass, and also the measurement of the proton-induced antiproton production cross-section, which is crucial for the indirect dark matter detection experiments. So for phase 1, they require the conventional muon and hadron beams, which will span between 2022 to 2025. And in phase 2, they will require conventional and RF separated hadron and muon beams, which goes beyond 2026. So the RF separated option is currently under study in our group. And we're also studying a high intensity hadron beam option, which is being studied in collaboration with the CERN radiation protection department for the Drelian runs. In my talk, I will focus mainly on the measurements requiring the muon beam, so the proton charge radius measurement. I should also mention that the AMBER phase 1 has been approved by the research board. The actual beam times are subject to separate approval as there are multiple proposals, so this will be done separately. So here we see the setup for the proton radius measurement, which includes the TPC of 2.2 meters, which will be filled with 20 bar of hydrogen gas, which acts as the target as well as the detector, with tracking in the beginning and after to track the scattered muons. So currently Compass occupies the EHN2 hall with a 55-meter long setup, which will also be required for the proton radius measurement. And in 21, they actually aim to do a test run with just the TPC and the tracking modules and 160 GeV muon beam, which would require a space of about 9 meters. So the studies and challenges, the most important challenge was if you will be able to run muon or Na64 mu together with Compass and AMBER. So the main questions that we had to answer was, is there enough space? Then are the physics requirements feasible? So whether the beam size and momentum requirements by these proposals are feasible in the EHN2 beamline. Also, if parallel running is feasible, as the beam times are quite competitive. So this was also a point of query. So studies were launched by the EHN2 sub-working group for the conventional beams and to address all these questions. So first, the question for, is there enough space? So here we see the EHN2 hall, and the Compass experiment currently occupies the 55-meter long EHN2 hall. And this would be required for the approved AMBER Drelian runs in 2022 and beyond. But upstream of Compass, there were 2 CDARs, which would not be used during the 21 run as they will use muon beams. So this freed up 13 meters of space without affecting the rest of the beamline. So this 13 meters of available space was deemed a feasible option for the 21 test runs. And this would not require any modification to the beamline as well. So here we see the 13-meter space once the CDARs are removed in a 3D model, and also the real beamline. So this is one CDAR that is still left. The other one was already removed at that time. And this is sort of the 15-meter space that is available for the test runs. So following 21 run, Na64 mu would require a space of 25 meters, and muon would require a setup of 40 meters. And AMBER, of course, requires the 55-meter long spectrometer. So in this case, the 13-meter space was not sufficient. But if we look at the beamline, if we remove the downstream magnets, then we free up about 42 meters of space. So this would then fit the requirements of the future phases for Na64 mu as well as muon. To reduce the changeover time, we have also foreseen installing a rail system, which would help the magnet and detector components installations. And all integration studies for the 21 run has already been done, and also the rail design have been completed. So next, we studied whether the physics requirements were feasible. So if you look at the M2 beamline, it's a 1.1 kilometer long beamline, which transports secondary particles from the target to the EHN2 hall. So here we see the beamline. The red lines are the quadrupoles, the blue ones are the bending magnets, and the cyan apertures show the collimators. So the M2 beamline consists of 700 meters of hadron section, which allows the hadrons to decay into muons. And then there is 9.9 meter of beryllium in a bend, which absorbs the hadrons that are left, and the muons just pass through. And the muon section is about 400 meter, which is present to select the final muon momentum and also clean the muon beam halo. So for the AMBER runs in the current Compass location, which is here, the conventional muon beam optics fits the requirements. However, the optics in the upstream location was not suitable for the test run requirements. So we studied 2 optic settings in this location. One for the focused beam option, which would fit the AMBER test run as well as Na64 mu, as they require a small beam size, and a low divergence beam option, which would fit the requirement of muon. So here we see the 2 optics options that were developed, one for the parallel beam with a divergence of 0.2 milliradian in both X and Y, and a beam size of 13 by 22 millimeter sigma. and a focused beam option with a beam size of 10 by 12 millimeter sigma and a divergence of 0.5 milliradian and 1.3 milliradian in X and Y, respectively. In both cases, the momentum spread was the same of about 6 GeV for 160 GeV muon beam. And these beam parameters fit quite nicely with the experiment requirements. Next, we also studied whether parallel running is feasible given the setup as well as the physics requirements. So if you look at the Na64 mu and muon setup, we see that there is considerable material. Na64 mu has the HCal and muon also has the muon filter. Now, when the muon beam passes through these material, it blows up the beam. So here is an example of the phase space in the Y coordinate at the entrance of the muon setup and after the muon setup, where we see the effect of the material which blows up the beam. Now, because amber downstream would require a focused beam, in principle, we can refocus the beam for amber, but for this, we would need the downstream quadrupoles. Now, if I can remind you that muon requires 40 meter of space and Na64 mu requires 25 meter, which would require us to remove the downstream quadrupoles. So this was not possible to do given the space available and the requirements. So therefore, parallel running was excluded from the results of the studies. Here I also show the tentative beam times up to LS3 for the different experiments. So Compass has their approved transversity run, which would go from 2021 mid to 22, and they have an approved run time of 150 days. For the proton radius test run as well, this is also approved for 20 days. The other measurements, the beam times are pending the SPSA recommendation. For Na64 mu, also the 20-day test run has been approved, and the rest of the beam time is also pending recommendation. Muon also has the test run approved for 20 days in 21 end. So just to conclude, there has been 3 new projects that have been proposed for the EHN2 Beamline in context of the PBC. That includes amber, muon, and Na64 mu. All 3 experiments have their test runs approved, and they will be running this year. We perform the feasibility studies in terms of space, beam parameters, and also parallel running. The space has been finalized as well as the optics options for the test runs. The parallel running has been excluded from the results of the studies. The integration of a rail system is also foreseen to reduce the changeover time between the setups. We are currently preparing for the 2021 test runs, and there are no showstoppers foreseen for now. The future studies will include higher intensities for Drelian, an RF separated option for amber, as well as the final integration of the muon and Na64 mu setup. And with that, I thank you for your attention, and I'm open to any questions.
Thank you very much, Dipan. So very nice talk, and questions for our speakers, for our speaker. So actually, I probably you saw it, you flashed it in your last table, like with timelines. Is it like, so you exclude the parallel running, right?
Yes.
So how long until when amber and muon can run to achieve these physics goals?
So the amber test run has been approved, and they will probably run around the middle of the year. For Compass transversity, this was approved already before, and they will also take a considerable amount of the beam time. So for now, the idea is to divide the Compass 150 days beam time between 21 and 22, and this frees up some time for the test runs. So Na64 mu and muon plans to go towards the end of the beam time, so around October, September, October, and before it will be the amber test run.
This is for this year, but so until when they are kind of envisioned to run, like you say, like 2024 plus, or?
Yes, so muon would need, as you see here, 2022 end, they plan to do a full setup run, hopefully. And then 2023 plus, they will do a 3 years of physics run. So this is sort of the runtime that they require for the statistics that they would like to collect. This is of course pending the SPSC recommendation, and the SPSC will decide how to divide the beam times, because of course the physics is quite interesting for all the runs. So this is still pending recommendation.
Thank you very much. Okay, thank you very much for this nice talk. So do we have Juliette back? Yeah.
Yes.
Juliette, are you ready?
Yes, I'm here. I'm
okay.
so sorry.
Now you can go on. So Juliette Mammei will talk about the status of the MOLLER experiment whenever you're ready. So Dipan, can you actually unshare? Okay, perfect.
Hold on a second. Too many windows open. Can you see my screen?
Perfectly.
Okay. So this ended up being a little bit more of an overview than just about the MOLLER experiment. So it's measurements of the weak neutral current with parity violating electron scattering. Oops, sorry. So parity is a quantum mechanical operator that reverses the spatial sign. We obviously can't apply the parity operator to our entire lab. So what we do is we generate an electron beam that has the spin opposite the direction of the momentum or in the same direction of the momentum. And we take advantage of the fact that the parity operator is not conserved in the weak interaction, though it is in the electromagnetic interaction. So a very brief history. In the 1930s, the weak interaction was needed to explain nuclear beta decay. In the 1950s, V-A theory was proposed to explain cobalt-60 decay, and the fact that the decay occurred more in one direction than another. In the 1970s, neutral weak currents were actually seen, neutral weak current events were seen at Gargamel. In the late 1970s, parity violation was observed in electron scattering at SLAC E122. In 1996, atomic parity violation was observed in atomic transition of cesium. And in 2005, there was the first measurement of the weak charge of the electron, SLAC E158. And in 2013, we had the first measurement of the weak charge of the proton, Q weak, at Jefferson Lab. And we keep pushing toward the precision frontier at Jefferson Lab and in Mainz to study these weak interactions. So as you all probably know, the electromagnetic interaction is a vector cross vector. The initial proposal for the weak interaction is a Fermi contact interaction, which has a form inspired by E&M, but then the V-A structure was needed to explain the Madame Wu's experiment. And it should be noted here that the weak process here is a charge current interaction. And in our parity violating electron scattering measurements, it's the neutral weak interaction. And the only way that we can tell that apart from the electromagnetic interaction is by manipulating the spin of the electrons to look for the parity violation. So in a lot of these experiments, we're looking for elastic scattering or molar scattering. So in this case, you have electron scattering from something denoted here by N. So N could be lead or calcium-48 as in PREX and CREX, which recently finished data taking, and PREX 2 will publish soon. It could be a proton or deuterium or helium as in G0 and HAPEX, where they searched for strange quark content of the nucleon, or it could be scattering from an electron as in the case of MOLLER. So we are generally looking for elastic scattering from nuclei, nucleons, or electrons, but you can also use parity violation in deep inelastic scattering as well. So how do you measure the weak piece in a parity violating electron scattering experiment? You're looking for this piece here. So this is a cartoonish way of saying the cross-section is a sum of the matrix elements squared, but you get this interference term where the Z exchange appears. And so if you form an asymmetry, many of the corrections cancel out and you're left with the term, which depends on the helicity of the incoming electrons. And for Q weak, for example, there's some kinematic terms out here, but the asymmetry was proportional directly to Q weak plus some hadronic terms. These asymmetries can be on the order of a ppm, but in more precise experiments, as time is going on, we're having to switch our unit to parts per billion as we become more and more precise. So here is a summary of a lot of the parity violating electron scattering experiments that have happened at Mainz Jefferson Lab and SLAC, including, also at MIT Bates. And now we have MOLLER, which will run soon, and soon is a relative term. And then in the future, we have SOLID at JLab, P2 at Mainz, and the EIC. So how we measure these asymmetries step by step is we have an unpolarized target and a high current, highly polarized beam. And then we measure a difference in the detector yields over the sum for the different helicity states. And we can use pulse pairs. That's how this is written, but we usually use quartets and sometimes even octets to calculate the asymmetries. These are very rapid reversals. Some experiments have used 30 hertz. Recent experiments have gone as high as 2 kilohertz. And the idea is that you want to take the measurements of the asymmetry on a timescale that is short relative to things that might be happening in the beam motion, beam energy changes, things like that. But we also have slow helicity reversals that can occur over a long time on the order of a day or so. Some experiments that run in halls A, B, or C at Jefferson Lab, and now there's a new hall D also, which is not pictured on this slide. They are counting experiments, and they don't, in the same way as the parity violating electron scattering experiments, consider the whole accelerator as part of the experiment. We need to control things all the way back at the injector because we're worried about false asymmetries that can arise due to helicity correlated beam properties. So we have to monitor the beam properties throughout the accelerator, as well as have active feedback to minimize the helicity correlations. So we produce the electrons in the injector, they're accelerated around to the proper energy, and then they are diverted into one of the 3 experimental halls. Q weak and G0 ran in hall C, HAPEX, and PREX, CREX ran in hall A. MOLLER will run in hall A. For the, all of these experiments require some sort of spectrometer. For PREX and CREX, it was the standard hall equipment, the high resolution spectrometers in hall A. For the MOLLER experiment, I'll show you, it has to be a special standalone spectrometer. Also, G0 and Q weak had to have special installation spectrometers as well. Oh, sorry, I forgot to mention, the spectrometers are needed to separate, provide kinematic separation because we are interested only in the elastic, elastically scattered or molar scattered electrons. But we do have to have background measurements and background detectors to correct for any backgrounds that may make it into our detectors. And in addition, something else that is required is high precision polarimetry. We need to know the polarization of the beam. It's a direct correction to the asymmetry that we measure to get out the parity violating asymmetry. So a lot of advances have been made in Compton polarimetry, which is a non-invasive measurement. We also use MOLLER polarimetry in the Hall, which is scattering the electrons from a polarized iron foil, and also a Mott polarimeter at the injector. But the Compton polarimeter can be used while the experiment is actually running, and so we can measure asymmetries. We can make polarization measurements at the same timescale as the actual asymmetries that we're measuring. So pulled together a few examples to talk about, and one of them is the helicity correlated beam properties. So the electrons are produced using a circularly polarized laser that's incident on a strained gallium arsenide photocathode. And this produces the polarized, linearly polarized, longitudinally polarized electrons. And then they're sent off to the accelerator. This is a plot of the quantum efficiency of the photocathode when it's new, and then a picture of the quantum efficiency of the photocathode after it's been used for a while. And you can see that there's a little bit of a hole that's been dug here. And so what can happen when the helicity of the laser changes, there can be a small position correlated differences, or even the size of the laser can change as you're switching the helicity. And that can change the position at which the laser hits the strained, the photocathode. And that can induce helicity correlated differences in the number of electrons that are produced. So this is not a parity violating asymmetry, it's a false asymmetry that can come into our data. So we measure positions, energies, and look for correlations with our detectors. And so we can measure and correct for it, not only positions, but angles, as well as charge and energy differences. And then we also have a feedback loop, which can automatically adjust things at the injector to make sure that we're minimizing our helicity correlated differences. So the result of the charge asymmetry feedback, for example, is that we can reduce the charge asymmetry faster with the feedback than simply by the statistical scaling. So average position differences at the target have been controlled to better than 10 nanometers. And just a fun fact, the width of a human hair is 50,000 nanometers. So, okay. So measuring all of these electroweak couplings requires experiments with different targets as well as different kinematic settings. So here I'm showing that you can get at the C1 Qs, which measures the Z exchange with the axial part on the electron side and the vector part on the quark side. And this is primarily using small theta, small scattering angles. And then the C2 Qs, which are the coefficients on the vector and axial vector pieces, are for V at vector on the electron side and axial vector on the quark side. And then MOLLER, for example, is with electron scattering. So the electromagnetic coupling is not parity violating, and the charge current violates parity maximally, but the neutral current coefficients need to be determined. So these C Qs, they need to be determined. So that's why Q weak measured the weak charge of the proton. and why the PVDIS measurements are measuring the other coefficient. But not only do those coefficients need to be determined, they haven't been determined. We can use these experiments to test the standard model. So with Q weak as an example, we measure this vertex at very low Q squared, and it's the parity violating part of the Lagrangian may have a new piece which has a possible new exchange particle X. And what we would be doing in Q weak would be measuring the coupling of that new physics to a proton. And in MOLLER, we would be measuring the coupling of new physics to electrons. And this is a picture or a plot of the sine squared theta W, which is the ubiquitous plot that we're trying to measure here when we're doing the standard model tests. All of these weak charges are proportional to the sine squared theta W, and that's the thing that we are trying to measure. It has a definite prediction in the standard model. So the blue line is the running of the sine squared theta W, and the blue band is indicative of the size of the theory errors there. For a long time, this plot was shown with the LEP and SLC points averaged together, but they actually disagree with each other slightly. So more recently, they've been separated out. And you can see the Q weak measurement here, which is consistent with the standard model. SLAC 158 is slightly above, and the relative errors of the future MOLLER and P2 is a Q weak, a more precise Q weak measurement, and then the future solid experiment. Okay, so I'm going to switch gears for a little bit to talk about the experiment. I am designing the spectrometer. I'm the head of the spectrometer group, so it's a little heavy on that side. So we have a target. It's a liquid hydrogen target. It's 1.25 meters long. It will be the highest power liquid hydrogen target. Q weak had previously set that record. The electrons are scattered and bent by a set of toroidal magnets, and they're bent out to the detector plane, which isn't shown here. It's an array of 224 quartz detectors, which are integrating detectors. We also have to have tracking detectors to measure our acceptance and shielding everywhere to try and minimize the backgrounds at the detector, as well as beam monitors that are in the beamline going, upstream to the whole accelerator. The nice thing about the MOLLER scattering is that you can maximize your statistical precision because 100% azimuthal acceptance is possible due to the fact that we have identical particle scattering. So the idea is that you accept the forward angle scatters on one side of 90 degrees in the center of mass, and then the backward angle scatters from the other. In fact, if you were to accept this one and this one, you'd be double counting. So any odd number of coils would work to do this. We block off half of the azimuth, and we accept from 6 to 9.5 milliradians in the for the forward angle scatters, and then 9.5 to 21 milliradians for the backward angle scatters in the lab frame. And then we put the detectors in the open sectors. There's a high lab scattering angle energy correlation. So not only do we have a large range of scattered angles, but a large range of scattered energies that have to be focused. And I use the term focused somewhat loosely. These are open, this Q weak, G0 and MOLLER are using open spectrometer ideas. So this plot is showing the magnitude of the field at the center of an open sector. This is all then the radially focusing component of the field. And it's showing particular tracks from the elastic EPs. The radiative tail would come out this way. And then this is showing the MOLLER EE focus that is our main signal. So we have an upstream torus, and we actually have, this is an old slide, I apologize. We actually have designed this downstream torus to have 4 different subcoils. So this is a picture of the rate at the detector plane. So it's a Y versus X. And you can see the MOLLER peak and the elastic peak. The detectors are, so this is zooming in on one septant. So a septant is defined between these 2 dashed lines. The MOLLER peak is segmented more than the other rings for various reasons, to study systematics and things like that. So each one of these rectangles is representing a quartz piece. And then you can see that here with a cutaway view, there's 224 of these quartz pieces. They're coupled to air light guides that go out to PMTs. And then we can read the yield for each helicity state. And this picture is from tests that were done at mines on prototype quartz detectors. So the science for MOLLER has long been demonstrated. We had a recent review, it's not so recent anymore, but we were recommended to proceed to CD1. And we have design and construction expected 21, 24, slipping a little bit. So first physics may be in 2026. And we have recently had successful NSF grants for a portion of the experiment in the US, as well as a successful Canadian Foundation for Innovation grant in Canada to build the quartz detector array. So the eventual uncertainty will be 5 times smaller than E158. And depending on the model of new physics that you're considering, with that uncertainty, we have sensitivity to mass scales between 7.5 and 27 TeV. And here's some plots comparing SUSY space. So there's RPV SUSY and minimally symmetric standard model. And it's showing the orthogonality of the MOLLER measurements and the Q-weak and P2 measurements from hydrogen. And then the plot on the lower right is another sine squared theta plot from Bill Marciano, which shows what this sine squared theta W curve could look like given a dark Z of different masses. Okay. P2, it will run at Mesa. It's a Q-weak measurement, which will include which will improve the precision on the measurement. Here they're using G instead of C, but these are the coupling constants here. And you can see that the blue is including the Q-weak measurement, and the cyan will be with adding the future P2 hydrogen experiment. They're also proposing the possibility of a carbon measurement, which would reduce this down to this red ellipse. And this is a concept of their detector, a superconducting solenoid. There's a person here for scale, and there's a Trankov ring detector after the solenoid. Solid is the a large acceptance device. It has a large acceptance, high luminosity, very small uncertainties. and it will enable a large Q-squared coverage. It contains the low energy backgrounds, has baffles to limit the backgrounds. There's detectors to measure the trajectories after the baffles, fast tracking, particle ID, etc. And they are planning to have precision polarimetry to 0.4% with Compton, and a atomic hydrogen MOLLER is being studied. At the Future Electron Ion Collider, I'm not sure how I'm doing on time. Sorry, I'm not paying attention at all.
That's maybe a good hint for our host. Sal, how would you like to keep it? Because we are currently almost 5 minutes behind schedule.
Oh, sorry. So,
Salvatore?
Yes.
How should we do it regarding time? Should we are 5 minutes behind schedule.
All right, let's go.
Okay, I'm almost done. So we are hoping to do parity violating electron scattering measurements at the EIC as well. And so here, my slides are numbered incorrectly. So this, I think, is my last slide. So there's a program to measure parity violating electron scattering for various different things, including testing the standard model. And to future measurements will search for beyond the standard model physics and to continue to improve our understanding of nuclear structure. That's my last slide.
All right, thank you very much. So we don't have time for discussion, unfortunately. So let's go to our next speaker, which is Cristian Pisano. He will talk about Gluon TMDs and J-psi polarization at the EIC. Cristian, whenever you're ready.
Yes, I'll try to share my screen. And then I will do the following. So can you see?
Perfectly.
Okay, very good. So thank you very much for the opportunity of talking about our recent work, which is still on progress and done in collaboration with Umberto D'Alesio, Luca Maciej, Francesco Murgia, and Rajesh Sanjan. Okay, I will start talking about first transverse momentum dependent distribution and factorization, a bit on general grounds. We know only 3 kinds of processes for which TMD factorization is being proven. And these are CEDs, so semi-inclusive deep inelastic scattering here, Drelian process, and E plus E minus annihilation into 2 light hadrons, all inclusive or semi-inclusive processes. And they are all characterized by 2 scales. A hard one, which for all 3 of them is the virtuality of the photon squared, and a small one, which is sensitive to the intrinsic transfer momentum of the partons inside the proton, which has to be much smaller than Q squared. And in the first process is the transverse momentum of the produced pion for CEDs. And then in the other 2 is the transverse momentum of the pair, the dilepton pair and of the 2 hadrons. And only when QT, this transverse momentum of the pair for Drelian and the 2 pions here is much smaller than Q squared, the R scale, then we can apply TMD factorization. So if we want to describe, this process is the QT dependence, so access the QT spectrum, we have actually 3 different scales. One is QT, then Q, the R scale, and then we have lambda QCD or an hadronic scale like the proton mass M here. And if we are in a region where the QT, for example, this is for Drelian, so the QT of the pair is much larger than the than the proton mass, then we are allowed to apply collinear factorization. In this case, QT is large and it's produced by the emission of a hard part, in this case, a gluon at the order alpha S. If you are in the low momentum scale, then we are allowed to use transverse momentum dependent factorization, and then Juliette will be given by the cross section. In this case, it will be given by the convolution of two transverse momentum dependent parton distributions. While in the other case, you use the usual collinear PDFs. But there is an intermediate region in which the two region, the high and low momentum transverse momentum region overlap when QT square is between M square and Q square. And in this region, you can use both approaches, and they all have to give the same result if they describe the same dynamics. So if the underlying mechanism is the same, otherwise, and in this case, you have to interpolate between the two results using the two frameworks. Otherwise, you have to sum the two results because they don't describe the same physics. So this scheme is useful, for example, for processes for which you do not know if TMD factorization applies. So for a process different from the three previous ones, and you want to check if your factorization formula is correct, or at least consistent. If you take the high QT limit of your TMD formula for the cross-section, for example, or any other observable, then you have to reproduce the result obtained in the high QT region, or better, taking the small QT limit of the high QT region. And this is what we do for quarkonium production in semi-inclusive deep inelastic scattering, because for this process, we don't know if TMD factorization holds or not. Yes, the point is that the three processes mentioned above, they are very sensitive to quark TMDs. And to access gluon TMDs, we need other processes for which TMD factorization has not been established yet. Concerning gluon TMDs, we can classify them according to a scheme which is very similar to the one for quarks. They even have the same names. And so we can organize them in this table according to the polarization of the hadron, of the parent hadron, and of the gluon. So I will focus mainly on the unpolarized TMD gluon distribution, F1G, and the linearly polarized gluon distribution. Both of them are accessible if we have an unpolarized proton target. And in particular, I'm interested in the linearly polarized gluon distribution inside an unpolarized hadron. This can be different from zero, provided that the gluon has a transverse momentum with respect to the parent hadron, and it is an interference between +1 or -1 helicity state. So it's a double flip helicity distribution. And it is a T-even one, exactly as the unpolarized gluon TMD. So this means that it doesn't need initial state or final state interactions in order to be different from zero, but it can be affected by this interaction, becoming process dependent. And because of the process dependence, which is encoded in the Wilson line, which are needed to make this object gauge invariant, you can have at least two different gluon TMDs, one in which both gauge links are future pointing. This is in processes like CDs, in which we have electron proton scattering into a color object. Or you can have both gauge links pass pointing, like in Drelian, when you have proton-proton scattering into some colorless final state. And because this distribution are T-even, they have to be the same. So the plus and the minus distribution, they have to be the same. And this is important to check. That's why we need to extract gluon TMDs both from electron-proton and proton-proton scattering. So we don't know much about gluon TMDs for the moment. We have just tried to extract an unpolarized gluon TMDs from only a few data points from LHCb collaboration. And yes, by looking at two J psis produced inclusively in proton-proton collision, assuming that the J psi are produced in the color singlet mechanism, this process has the same gauge link structure of Brilliant. So proton-proton into two colorless object. And so this is a very preliminary study because only 4 points in a very simple Gaussian parameterization. But and then the other distribution, it's very interesting because it can modify the PT spectrum of scalar and pseudoscalar quarkonia, for example, like eta C or chi C in a different way with this opposite sign here. So it could be accessed in future experiment like fixed target experiment at LHC and NICA, for example. But here I will focus on the EIC and on quarkonium polarization. So this was for scalar and pseudoscalar quarkonia, but we can do something also for J psi, which is more abundantly produced. So we study essentially semi-inclusive deep and elastic scattering in which we produce a J psi in the final state. And since we want to look at its polarization, we study this process in the rest frame of the produced quarkonium. So there is not a unique choice for the frame. So we have studied this process in 4 different frames, depending on the choice of the Z axis. So the quarkonium is at rest, and you can define the X, Y, and Z axis according to the momenta of the incoming virtual photon and proton. And they are all related by rotation around the Y axis. So then we can use some model-independent arguments like hermiticity, parity conservation. So without specifying the frame, either collinear QCD factorization or TMD factorization. And we are led to 8 independent helicity structure functions, which are written here. And here the superscript P means the polarization of the incoming virtual photon, can be longitudinal or transverse. And the subscript refers to the helicity of the produced J psi. So it can be transverse, longitudinal. Delta is a single helicity flip, so interference between helicity 1 and helicity 0. And this is the double helicity flip, which is the object we are more interested in. Although these are 8 objects, you cannot single them out entirely by just looking at the decay of the angle at the angle of the decaying leptons, because you can access only 4 linear combinations of them. So where the polarization of the photon is always summed. Okay, in principle, you can kinematically distinguish cases in which Y is very large, and then you can get essentially WL lambda, and vice versa. When Y is very small, you can access the other one. But if you then calculate the cross-section in terms of the usual series variables, you find this result. So you can disentangle only these 4 objects, and in particular the double helicity flip is related to the cos 2 phi dependence, so where phi is the azimuthal angle of the decaying lepton for the GCL. Usually it's more common to write these 4 structure functions in terms of the polarization parameters lambda, mu, nu. And then our object will be the new polarized parameter, so sensitive to the double helicity flip. At this point, we can specify the framework and decide when Qt is large, then you can use collinear factorization, and we calculate this process at the order alpha s squared. And within the framework of NRQCD, which consists in a double expansion in alpha S and V, the relative velocity of the heavy quark pair produced in the scattering process. And you can have then different partonic sub-processes, which are depicted here by these diagrams. And only the 6 ones, which corresponds to this Feynman diagram A, correspond to the color singlet production mechanism. In fact, according to NRQCD, you can produce the heavy quark pair both in the color singlet production mechanism or in a color octet state, which then subsequently decay in a color singlet object, which you observe the J psi by emitting soft gluons. So we have included all these Fox states up to order VA⁴, and this is the state of the art. And actually, we think this is the very first time that quark-gluon polarization within an NRQCD has been calculated at this order, even in collinear factorization. And we use the calculation of Benecke and collaborators to learn how to use an RQCD in order to calculate polarized structure functions. But they studied the photoproduction, so our process is Q² different from 0. And now if we have this result and we define QT, so the transit momentum of the virtual photon with respect to the momentum of the J psi and the incoming proton, we can study the limit in which QT² becomes much smaller than Q². So we can take this limit. Actually, we calculate the previous results in all 4 different reference frames, and the analytic expressions are complicated. But if we take this limit, so we go in the intermediate overlap region that I talked about before, then the structure function become very simple.
You got 3 minutes, Cristian.
How many? How many minutes?
3 minutes.
3? Oh, perfect. 1 per slide. Yes, so the expressions are very simple now, and many of these helicity structure function have a dependence on the logarithm of the Hart scale divided the QT scale, and these are convolution of the usual collinear PDFs with the usual leading order splitting functions. But what we are interested in is this object. The double helicity flip doesn't have any logarithmic divergence. And all these cross-section are contain the color octet long distance matrix elements of an RQCD, because they all come from these T-channel diagrams, which exist only for the color octet. And then we can do the same in using TMD factorization at order alpha S. And then we have just this simple diagram and the crossed one. And here again, we can calculate the same structure function, and the result is very simple. It's just a product. If we neglect smearing effects in the final state, the structure function are just the product of the cross-section, partonic cross-section with the TMD dependent, with the TMD gluon distribution. In particular, the double helicity flip structure function will give direct access to the linearly polarized gluon distribution and to this polarized cross-section, which contains only the 3p0 long distance matrix element, which is also not very well known. So measurements of this object at the EIC, for example, this process in the TMD region can give access to unknown, basically. The H1 perp G distribution and this color octet long distance matrix element. The last slide before the conclusion is that we cannot ignore, if we want to write a factorized formula in terms of TMD and hard part, as we're trying to do, we cannot ignore the smearing effect, which I talked about, and this emerged in the calculation of the first helicity distribution. If I take the high QT limit of these results, they will match with the collinear results that we just calculate in the overlapping intermediate region, only if we substitute the TMD distribution with a convolution in terms of momentum of some shape function which encode the smearing effects. These are like fragmentation functions, but for Qualcomm production, or if you want, they are the TMD generalization of long distance matrix elements of QCD. And just to close, I tell that this is consistent with another similar analysis which we did for unpolarized Qualcomm production. And we, by imposing this matching between TMD and collinear calculation, we obtain the perturbative tail of this shape function, and it's consistent with previous results by ourselves and also by other groups, obtaining a different way. So to conclude, summarizing, polarization states of J-psi meson produced in semi-inclusive deep elastic scattering can be studied at different frames at TIC. In the TN region, we have shown that the distribution of linearly polarized gluon can affect the new polarization parameters, so the double helicity flip structure function. And we have correctly checked that the TMD formula for these 4 different helicity distribution, they match. The calculated order alphas, they match with the collinear factorization results at high transverse momentum at the order alpha squared. So the TMD at order alpha s has to match the collinear at order alpha squared. Only if we include also shape functions, but this was expected from our previous calculation. So if EIC data will come on this process, then we will be able to understand more about gluon TMDs, in particular this unknown linearly polarized gluon distribution, shape functions which are completely unknown, and also the mechanism which underlines Qualcomm production and polarization. For example, the size of these 3p0 long distance matrix elements. I just finished reminding you that there are other studies using basically the same process, inclusive Qualcomm production at TIC, but looking at different observables, like unpolarized J-psi usually, and different frameworks. For example, for the production mechanism, you can use color evaporation model instead of an RQCD. So there are really lots of theoretical studies, and it would be nice to have also data very soon. Thank you.
Thank you very much, Cristian. Questions for Cristian? No questions? So the talk was very clear. Thank you very much. Yeah. So next is Jakub Wagner, and he will talk about the exclusive production of charmed meson at the LHC.
Good evening, or good afternoon, whatever applicable at your time zone. Do you see my slides?
Yes.
Okay, good. So the title of my talk is Exclusive Electroproduction of Charmed Meson at EIC. And if time permits, I will also add some remarks on the neutrino production of the mesons. So this is based on the recent paper with Bernard, Pierre, and Lech Szymanowski, which appeared early this week on Archive. And you can see the reference here. Okay, so what is the context? The context is that we are interested in exclusive processes, and we know that there are many channels, so we need all of them because GPDs are very interesting, but also very complicated objects, and we need a lot of independent measurements to know as much as possible about them. So we know that we have deeply virtual Compton scattering, we have deeply virtual meson production, we have time-like Compton scattering, heavy vector meson production, a lot of exclusive processes that we can use to learn something about general Spartan distributions. Also, the charge current were considered, and specifically charge current production of light mesons, and there are references below. And this is very interesting because that allows for flavor separation using different mesons, but also you get the different combination of GPDs due to different charge current coupling structure. Of course, the cross sections are much smaller, but the processes are in the reach of the some next generation neutrino experiments for neutrino production or electron ion collider, high luminosity machines for electron production. So in this study, we were calculating charge current exclusive production of charmed meson. This is very interesting process because we have heavy quark mass, which allows us to extend the range of validity of collinear factorization. We do not have to stay in high Q square, but heavy quark mass itself gives us a hard scale here. So there are some factorization theorems with heavy quarks, which were proved independently on the relative sizes of Q, so the virtuality of photon and quark masses, when the Q square plus charged meson mass square gives us a hard scale needed for the factorization. So in our calculation, we included charm mass in the propagators, but also we have included charm mass, meson mass in the definition of distribution amplitude. We use this decay constant, which recently calculated on the lattice, and we use some two different parameterization proposed by two groups for the distribution amplitudes, and this is shown on the figure. This is slightly asymmetric because of the asymmetry within heavy and light quark. Okay, so here are the diagrams that are needed to calculate the electroproduction of charm meson. You have heavy quark line represented by this thick line, and we know that the amplitude will be proportional to Kabiba-Kobayashi-Maskawa matrix elements. So the dominant channel will be the DS minus or DS star charmed and strange mesons. Okay, so here is a differential cross section for such a production. This is a known formula. We have those sigmas here, which are product of amplitudes for certain polarization. You have a Fermi constant here, so you see that this is really a charge current, and then the cross section has to be a little smaller. So we have calculated gluonic contribution, and there is the amplitude for gluonic contribution. You see that term here, which comes from the conversion of the strength tensor in the definition of GPD to the gluonic fields. You have a distribution amplitude here, and you have GPDs here and there and here and there, and you also have those blue hard parts, hard coefficient functions. So this serves to definition as a definition of generalized form factors, which are shown here. Okay, so our hard parts and are symmetric and anti-symmetric. I do not write the numerators, which are pretty complicated, but it's worth to look on the denominators. Those denominators comes from the quark propagators, and what is worth seeing here that there is not only x minus psi here, but there is a shift in this alpha and beta, which are defined here and which are proportional to the charm mass. Okay, so for the pseudoscalar, after we integrate over these azimuthal angles, we are only left with those two terms, and for pseudoscalar, this transverse part vanishes, and we are only left with this longitudinal part, which is given here as some combination of those generalized form factors, including gluonic GPDs. And here are the results. So this is the result from for the S equal 820. GeV square for lower energy of EIC. And we see that those numbers here are not very impressive. This is of the order of 10 to minus 3 of picobarns. So on the left-hand side, there is a cross-section as a function of Q square for 3 values of y equal 0.2, 0.5, and 0.8, but they are all pretty low. And here I show the same, but for the S equal 20,000 GeV square for higher energy squared. And here we see that those numbers are a little bit more optimistic, and we have some cross-section, again, as a function on the left-hand side, and it's a function of Q square for 3 values of y. This time y is 10 to minus 3, 5 times 10 to minus 3, and 10 to minus 2. And this time this is on the order of picobarns. And here on the right-hand side, you have the same on the function as a function of y for Q square equal 0.1 GeV square. Okay, so this was for the pseudo scalar, and okay, here I also present some dependence on the model that we are using. You can use different GPD models. You can use different DA model, and here the solid lines are for this DA proposed by Kurimoto and al, and dashed line are for the DA proposed by CERN et al. And blue lines are for the Golodkov-Kroll model, and the black line are some simple factorized GPD model just for comparison. So we see that we can somehow see the dependence on the models used, or sensitivity of this measurement to the different models. Okay, so that was for pseudo-scalar meson, and we also have calculated that for the vector meson, and this now have 2 parts. Okay, so this vector meson mostly decaying into this pseudo-scalar plus photon, and these have 2 contributions. So the longitudinal amplitude is more or less similar to okay, it is up to some trivial changes in masses and couplings. It is the same as for the pseudo-scalar, and main difference comes from the fact that there are some higher values of skewness, so the smaller values of gluon GPDs. And the transverse part consists of 2 components, and one which is which depends on chiral even GPDs, which contributes to this azimuthal integrated cross-section, and other part which just depends on transversity gluon GPDs, but this depends on this does not survive the integration of the azimuthal angle. So here are the results, and on the left-hand side, this is the longitudinal contribution. On the right-hand side is transverse one. So we see that this longitudinal is a little smaller than for the pseudo-scalar, but on the same order of picobarns, and it dominates over this transversely polarized amplitude. Okay, so that was for electroproduction. I also wanted to add some remarks about the production of the neutrino beams. And for that, we were studying production of the D+ and D0 meson. And that was also studied previously for light mesons. So the longitudinal amplitude, it's more or less small modification of the calculation, which was already known before. Again, we have some amplitude parameterized by those generalized Compton form factors, and those generalized form factors are given by this factorization formula with distribution amplitudes and quark, d quark this time GPD. But this part also have this amplitude also have a transverse part, and this transverse part is interesting because it depends on the transversity GPDs. So here again we have those generalized form factors, but this time they depend on the transversity GPDs for quark. So here is the longitudinal cross-section, which now is very similar to what I shown previously, but now it contains also quark and gluon contributions, and we see that those cross sections are indeed very small for S equal 20 GeV. But we see that the gluon's contribution is important. You cannot neglect gluon contribution. It's as important as quark. And here is this other interesting part, which depends on the gluon on the quark transversity. And we see that we have some signal and some handle on the transversity GPD2s in this neutrino production process. You have also the interference term between transverse and longitudinal part, and we can study some azimuthal dependence of those terms, and we can project them out by some moments of, for example, cosine phi moment projects out this real part of this interference term, and sine moment projects out this imaginary part, and this is proportional to this combination of GPD, and you see that you have a transversity GPDs present here, and here there is this azimuthal dependence shown, and this is direct measurement of transversity GPDs. It will be called 0 if there were no transversity GPDs, and here it is shown prediction for this cosine moment and sine moment, which are proportional to the real and imaginary part of transversity of some combination of GPDs, and this recurs for every moment depend on some more different models of transversity that we have used. So we have some sensitivity to the models that we have used. Okay, so I arrived to my summary, and what I was presenting was the charge current production, exclusive production of charmed meson, and we see that the collinear QCD factorization allows to calculate this charge current production of the mesons down to Q² equals 0 because the hard scale is given by the charm mass. And for this charm mass electroproduction, we have shown that the cross section, although small, are in the reach of the future high luminosity electron ion colliders. And indeed, they have the same order of magnitudes as for the light mesons, but for the larger Q² values. Of course, one has to think how to detect those channels, study the decays of the D meson and so on. So there is a feasibility study needed here. And also I have presented the neutrino production of the charm meson, and we see that we have different contribution for chiral odd and chiral even GPDs. And we can use azimuthal dependence of cross sections to get access to chiral odd transversities. We can also study different behavior on the proton and neutron target, and we can separate U and D quark contribution, and that should be in the region of some future high energy neutrino facilities. Okay, thank you very much.
Thank you very much, Jakub. Questions for Jakub? Actually, I have one. You often say that, you know, the cross sections are very low, but they are within reach of the EAC. Can you actually quantify a little bit better how much luminosity you could need to, you know, for the precision you need to extract these cross sections? For example, the plots that you show are often with one beam in Q². So I kind of have a hard time to gauge actually how much within reach they are. Okay,
that's of course a very, very preliminary study for this electroproduction. That's the first time we've calculated and we have not pursued it farther than what is presented here. So this is of the order of picobarns. That's what I only thing that I can say. Okay, and I know that it's difficult, especially later when you have to deal with D meson, right? It's just a production of D meson, and that has to be complicated. But that's why it's in a future experiment session, I would say. But this is these picobarns were pretty encouraging for the charge current processes, right? This is usually something that you should expect here.
All right, thank you. So I think like some further investigation is actually needed here to.
No, we are trying to convince some more experimental oriented people to have a little bit deeper look on that.
All right, point taken. Thank you.
Thank you. Salvatore, we can't hear you now.
Sorry, I muted myself. So next speaker is Maciej Trzebinski, and he will talk about the overview of the Atlas forward proton detectors for the LHC Run 3 and plans for the high luminosity LHC.
Hey, hello,
Please
can you hear me? Can you see my slides?
Yes, we can.
Okay, good. So very briefly about the Atlas Raman pod detectors. So first, let's start with the physics that we are interested at. And of course, you can, let's say, divide it in many ways. What I did, I just distinguished the hard processes and soft processes. And then in hard processes, you can have those of non-diffractive nature and the ones of diffractive nature, which, to say it very roughly, involves exchange of a colorless object, either a photon in case of electromagnetic exchange or a so-called pomeron in case of, well, hard, QCD, so in case of strong interactions. And then, of course, soft processes also can be non-diffractive and diffractive. So there are two methods to seek for a diffraction. So when you have your detector, which is sketched in here, well, the diffractive event will feature in two topologies. So actually, one of it is a rapidity gap, which is a space in rapidity devoid of any particles produced. This is a usual method for diffractive pattern recognition. You don't need anything else except your central detector, but this gap is in very forward region. So, well, either it might be outside of the acceptance, simply majority of the gap is in the beam pipe, or it can be killed, for example, by pileup, especially in the regions when you don't have trackers. Then you have the second method, which uses the fact that in diffractive process, the proton should stay intact. So you can measure it or measure them, as actually both protons can stay intact as well. So these can be used in pileup environment to some extent, depending on the event. But you need additional forward detectors, which has to be very far away from your collision point due to the very small angle at which protons are scattered. So in Atlas, in fact, we have two such sets of these detectors. One is called alpha, which stands for absolute luminosity for Atlas. These are located around 240 meters from Atlas collision point. They're mainly for special runs with special LHC settings, and they are mainly for the elastic scattering and soft diffraction measurement. These are tracking detectors with resolution roughly of 30 microns. And then a bit newer system, which operates since Run 2, which is Atlas Forward Proton, 210 meters from the Atlas interaction point. This is mainly for hard diffraction, exclusive production, and new physics searches. It can take data during the nominal runs, so you can expect even femtobands of data with such detectors. It has tracking devices and time of flight detectors, and about this I will say in a few moments. Now, just to say, there are no major changes between Run 2 and Run 3 detector setup. So if you take, let's say, TDR, the description of the detector may be just a little bit outdated, but in general valid. A word about why, you see, if we need to do proton tagging or really have to do a position measurement. Of course, tagging provides information that the proton is there, but actually with the measurement of the position, and actually if you have two detectors, you can measure the position and also elevation angle, then you can develop a method which would allow for unfolding. So then from the position at the detector location, you can say something about energy and transverse momentum at the collision point. So in other words, from the position measurement in forward detector, you can say something about the energy happening in the collision, which is a very strong information and also very powerful constraint when differentiating signal from background. So this, in case of AFP, position is measured by silicon trackers, which are 3D silicon detectors with a pixel size of 50 times 250 microns squared. And well, since we have 4 layers which are staggered, so shifted one with respect to each other, the overall measured resolution is around 6 micrometers in X. This is X is a shorter pixel direction, and 30 microns in Y. And these detectors can also provide a trigger in the low pileup environment. In alpha, we use another technology, which are scintillating fibers. So we have in total 20 layers per let's say, detector. And the precision with this setup is something like 30 microns in X and Y. Then in AFP, we also have a time of flight detector, and the purpose is mainly to reduce the physics background, because you can imagine if your signal is, as on this picture on the left, 2 jets and 2 protons, we call it an exclusive jet production, then you can easily imagine that such will be mimicked by non-diffractive jets, which has cross-section, which is like 6 orders of magnitudes higher, and then overlaid with protons coming from pileups, so some independent minimum bias interactions. And if you have a time of flight, so if you can measure the time of arrival of these protons to your central detectors, if you can correlate them with the information about the vertex of your hard event, then this is also a very powerful constraint, which allows you to reduce background by more or less order of magnitude when your timing precision is of around 20 picosecond, which is quite significant reduction. In AFP, in order to do this, we use so-called time of flight detectors, which are in the, well, they use quartz bars oriented in Cherenkov angle, and then once proton is crossing these bars, the light is produced, and then it's read out by the photomultiplier. And actually, I will show you that indeed we have resolution of around 20 picoseconds with those, which is, well, actually one of the best people can achieve so far with such devices. So I would like to mention that these 2 subsystems are merged since 2 years now into the Atlas Roman pods. That's the title of this talk, Atlas Roman pod subsystem. And in fact, they are, as we are in the so-called LS2, in the, let's say, maintenance period, there are some improvements ongoing. I will not go into details, but they are a series of things, small changes in design, optimization, and so on. So there is a significant amount of work done by our colleagues. We also work on the performance, right? Because with these detectors, the measurement is not easy. We have to take into consideration the magnetic field of the LHC, all of the magnets which are between Atlas collision point and our detectors influence obviously the proton trajectory, the detector alignment, trigger, and so on. So that's why we have a dedicated task force for that, which we called Proton Combined Performance Group. And well, actually, this group is doing really well, providing the proton object for general analysis. I mentioned about the time of flight. So again, I will not go into much of the details, but I refer to the public node that we have. In principle, with the setup that we had in 2017, we achieved a very, very good resolution of about 20 picosecond in one side and 26 picosecond on the other side. We suffered from the very low efficiency, and actually more is in the flash talk given by Tomasz Komarek, so you can see more of the details, and of course in the note I quoted. Then just one slide on the analysis. This is the first measurement we've done with AFP about exclusive dileptons. And as you can see, the possibility to have proton tagging introduce very powerful background rejection. So as I mentioned, this is not only proton tagging, but also a proton reconstruction, which allows for kinematic match of proton versus lepton system. And we measured cross sections for such processes of proton-proton going to EE plus proton and mu plus proton with quite nice precision. Plans for run 3. Well, AFP will take data during standard runs, and we hope for more interesting analysis similar to exclusive dileptons, and also for some physics searches. But also there is a very interesting opportunity foreseen for alpha. So if the beam energy of LHC will increase with respect to what we had in run 2, it would be very beneficial to have another point to measure the total elastic and inelastic cross sections at new energy, because we have struggles, we have some discrepancies with the measurement we did so far, also some discrepancies with what our colleagues from Totem measured. And in addition, we should be able to determine rho parameter and so-called elastic slope. So there is ongoing work for, because for such type of measurement, you need special arrangements, special preparations from the LHC machine side. One slide about run 4. So you may saw that our colleagues from Totem released the expression of interest for the Roman pods being installed at the high luminosity LHC. In Atlas, so there is ongoing internal discussion about this issue. We are determining building a physics program, and just to show you that there potentially these such measurements are very interesting. And well, if you are more interested, the reference are here. So in a summary, well, with alpha, we have many new elastic and diffractive analysis on the way, so please stay tuned. I was not talking about this because this is supposed to be more of a technical talk, not a physics talk. Alpha is ready for commissioning, and well, if the energy will increase to say something like 13.5 TeV in the center of mass, well, this will be a very interesting data to be taken during the special run. For the AFP, lots of analysis of diffractive and exclusive hard events based on run 2 data is ongoing. The results should appear soon. The first result is already there, so I just briefly mentioned it. With half of the detector system we are ready, is being commissioned. Other so-called far station, which have new this time of flight system, should be installed during the summertime, and actually they suffered COVID-19 as well. Travel restrictions and supply chains were kind of, well, you know it. So for run 4, the program is being discussed within Atlas. Now, if there is a positive, let's say, decision by the collaboration, then further steps like actually the preferred detector localization and actually technology, probably even more precise, better that we are using now, and some optimization of optics, so settings of LHC magnets can be considered. So, thank you.
Thank you, Maciej. I think it's a very nice program. Questions from our audience? Everybody's shy today. So I actually have one, and is it like, okay, probably you just mentioned it in one of your last points here in the summary, but I wonder if, like, with the high luminosity LHC, is that impressive already, 20 picoseconds of timing that you actually mentioned, enough to deal with the pileup? I think it's a huge pileup. You have like thousands of events or so, correct me if I'm wrong. So what kind of actually timing you envision?
Thousands is of course is a bit too much, but yeah, there are various scenarios of pileup. I heard numbers between 100 and something like 600 or so. Right, we will have to deal with that as well of the rest of Atlas subsystem. Now there is really no limit, right? The faster your detectors are, the better your, let's say, more powerful background rejection would be. If 20 picoseconds will be enough. Well, if the 20 picoseconds is the best we can have, we will have 20 picoseconds. But actually our aim is to do better. So we are thinking of 10 picoseconds or maybe even less of detector resolution, but this would require more R&D, especially on the readout side.
So what could you use for achieving like 10 picoseconds? What kind of technology?
Yeah, for example, our readout TDC is now a bit slow, and there you have just extra couple of picoseconds to be added. Under development is something which we call the Pico TDC, which should be as fast as 1 picosecond, right? So it's like a factor of 10. So this is one of the examples of the readout electronics which can be improved.
Basically, only on the readout electronics that you are dealing for.
Well, if we are talking about, of course, the system with the Cherenkov bus and photomultiplier, right? Of course, photomultiplier also can be improved. This is external companies that they are doing this, Photonis and Hamamatsu. They have to meet these harsh requirements. But also to mention that this is not the only technology possible, right? You can have the LGAS, or you can have the diamonds, right? They are now not that fast. However, with LGAS and diamonds, you can have much more layers inserted. Like
I think also the LGAS, like 20 is really near the threshold that you can achieve at least currently. I think, I don't know if in the future they can go lower, but okay.
So yes, I mean, when there will be a decision about Run 4, there will be also, I would expect, very fruitful discussion about which technology actually to be used, and then I would expect that groups which are developing will show their best to convince us.
My last question is actually, when do you expect such a decision from the Atlas collaboration?
Right, so I cannot really say for the Atlas collaboration, right? But I would say the sooner that, well, from the machine point of view, the preparations for Run for high luminosity LHC are ongoing, and things are booked, for example, in the tunnel and so on. So the answer is, of course, the sooner the better. If we can have some consensus this year, this would be perfect in my opinion.
All right. I wish you good luck with that. So thank you very much. And let me take this opportunity to thank all our speakers in these 3 days. It was a nice packed session, very dense and very diverse. So thank you very much, everyone, for participating and attending this session. Thank you. Have a good afternoon or night, wherever you are.
Thank you also from my side, and thank you for moderating, Salvatore.